Hi class, welcome back to Electromagnetics. So with this lecture, we're going to start part 9. This is the final section of the course. We're going to change gears just a little bit and look at the Hertzian Dipole. So inspirational thought for today, something a little different, not a direct quote from scripture, but a saying that, gosh, if you ever worked with me, you'll hear me say it pretty often because I think there's a lot of truth in it. And that is that experience is what you get when you don't get what you want. And so I use this often with younger engineers, and I hope that it comes across as an encouragement because, you know, that's the one thing that will increase your value in industry is to have experience. But there's no shortcut to getting experience, right? There's no fast track. It just takes time. And oftentimes we get the most experience when we have situations that things don't go the way that we expected them to go or that we thought they would go. And when that happens, you know, we've got to back up and we've got to figure out why it didn't happen or go the way we wanted it to go. Well, it's in those moments that we gain the most experience. We learn something pretty valuable and helps us the next time. So let that be an encouragement to you as you enter into your career. You know, when things don't go the way you want, you know, don't get overly discouraged. Just realize that this is an opportunity for you to gain some pretty valuable experience, because experience is what you get when you don't get what you want. All right, so part 9, antenna basics. You know, you can take entire courses on antennas, and I have taken a couple. Usually there's graduate level courses, but you can sometimes take them as electives as seniors at some universities. So as you can imagine, this is going to be a really abbreviated coverage of that. I just wanted to give you some highlights of antennas so that you know, you can have some tools in your toolbox. And as you maybe go into grad school, you know, you can help you make choices if that's the field you'd like to go into. So, like I've alluded to in the last couple of sections, we've been focusing primarily on the propagation of electromagnetic waves, and that entails different scenarios and different aspects and different ways to do that. But for this last section, I do want to turn our attention or shift gears a little bit, like I said, to sort of propagating EM waves, radiating electromagnetic waves. So we've already touched on this just a little bit back in section 4 when we had our infinite current sheet. You know, this is what was actually happening. From the current sheet, we were propagating an electromagnetic wave. Of course, this was not a practical application. Now we want to look at something that's a little more real world or practical, and that's the use of antennas. And so when we do this, though, we're not going to have that clean mathematic model of the infinite plane wave. We're now going to have this finite plane wave, or finite waves, and these are going to be fringed, and we'll look at an example of that in just a minute. All's not lost, though. A lot of what we derived already using that theoretical model can still be applied for most cases, or can be easily modified, and so that's what we call these new finite sources we're dealing with, antennas. I want to start our discussion with this super simplistic model, okay, and we're going to first consider this infinitesimally long piece of wire that can carry an alternating current. And we're going to find that current with this equation here, just a simple sinusoidal wave. It'll have a magnitude of I sub 0, and we're going to think of that in terms of this group charge Q1 of t, and then we're going to have this on the opposite end, the polar opposite end of it, QT, which is just the negative of that. So it's going to be out of phase 180 degrees, or negative Q1T. And we're going to see these separated by this infinitesimal unit length dl, and that's what produces this current I sub t as they're going back and forth in opposition to each other. So from that, we can now come up with some mathematical definitions to model this. So our current is going to be our change in charge over time, which that's our basic definition. So we can equate this differential change in charge with respect to time as our current. And then dq2, of course, is the negative of that since it's out of phase by 180 degrees. So from this, then, we can just do the simple integration here and derive expressions for our charge Q1 of t and Q2 of t. And as we expect, just doing simple calculus, this will be our magnitude current divided by the frequency, sine omega t, and then the negative of that for q2t. So one thing to kind of note here is that as we increase the frequency, our amplitude will decrease. And so that's something, if you get into antenna theory, you do have to deal with a little bit. So if you look at a graphical model of this, this middle graph is our Q1 with respect to omega t. And so you can see it's just a cosine wave. And then our Q2 is the negative of that, 180 degrees out of phase. So like I said, they're going from one end of the wire to the other, passing each other as they go. And so from that, we can also derive our current. So the current is the derivative of that. And so when we look at that, it's maximized here. And then it's the same type of sinusoidal wave. It's just out of phase by 90 degrees, and we see here. And then you can think of it as the charge. So as there's no charge at each end of our antenna, the current's maximized, right, as the charge is flowing from one side to the other. But as the charge builds up at each end, we see that that current starts to decrease until the maximum charge is at the ends, and then there's no current there theoretically. So that's why there's a zero here, and these are maximized. So that's this little graph at the top is kind of showing you what's going on in our infinitesimal antenna. So let's take a step back here now, and then we should have some feel for this now with all of the electromagnetics that we've been exposed to in Maxwell's equations. And so we should recognize now that there should be an E field due to the charge itself, and then there should be a magnetic field or an H field because there's moving charge, right? And so we also should recognize that this should generate an electromagnetic wave that should be generated or radiated from our antenna. So because of this, hopefully we should have some idea of where to start with our electromagnetic analysis using Maxwell's equations to derive expressions for these electromagnetic waves. So we want to do that now. We want to start by characterizing the electric field just at some arbitrary point from our antenna, and we need to have just a graphical model to help us do for the framework of this. So let's look at that on the next slide. So here's that model. So here's that model, the antenna that we looked at earlier with our Q1, negative Q1 or Q2, and they're traveling back and forth as DL. And so we're going to pick this arbitrary point out here, and you can see that we're up into the Z-axis, and we're out over the XY plane by this dashed line, so it's just truly arbitrary out here. And so if we were to take the center of this antenna, that's this distance R, and so that's what this unit vector AR is in that direction. But we also need to keep in mind this R1 and R2, and that's from both of our endpoints on the antenna. And so we have corresponding AR1 and AR2, which are both in those directions. And then since we know this is going to be a transverse wave, we have this A phi and A theta, which those are perpendicular to each other, but they're also perpendicular to this A sub R. So these are kind of like our X, Y, and Z planes that have been shifted around. Instead of X, Y, and Z, we've now got AR, A phi, and A theta. We also need to be aware of these angles, alpha 1 and alpha 2, that the R1 and R2 make with R. We've got this theta down here, which that's the angle R makes with the Z-axis. And then we've got this theta, which is the angle that's lying in the XY plane, that this angle here, the projection of the XY plane, makes with the x-axis. And then from that too, we can also derive some distances, this dl cosine theta, and of course we're going to have permittivity and permeability of our medium. So we should have all the tools in place we need now to come up with some mathematical expressions. So from this diagram, it is using really basically the equation we got from physics, not even electromagnetics. We should be able to come up with basic equations for the electric field at that point. And so what we have is just the charge over the 4 pi epsilon radius squared. So we have the R1, AR1, And then for Q2, it's R2, AR2. And we can define this AR1 and AR2 just using simple trigonometry, which we've done this before in part 8, showing how we can come up with these unit vectors. So from this definition, we can use this our vector algebra and some strategic substitutions, and we can obtain general forms for these equations for this electric field at this arbitrary point. And this is what we come up with. Likewise, we can use the Biot-Savart law, and we can obtain an expression for the associated magnetic field at the point P, which is this equation here. So I don't want to go too deep into the theory. Like I said, this is an introduction to this, so you're going to have to just kind of trust me on this, but feel free to go back. You should have the tools to derive these without any problem, but this is the final equation. I didn't want to spend time on that in this section. I'd rather do it on the application of it. So now that we have expressions for the electromagnetic fields associated with the charges in the current element, we now want to extend our analysis for the case when the charges are time variant. So again, this is stationary charge, right? Or the stationary points, I should say. But we got to think about this all along the antenna, the infinitesimal length. So to do this, we need to make a few quick adjustments to our equations, these two equations on the next slide. Here you can see we've done that, and it's basically in this numerator, and now instead of looking at the charge, we're looking at that current and that distance dl, and then the time variant piece for that. So these are the equations we've come up for our electric and magnetic fields that are radiated from the antenna. And these will all be fine and good, right? Except there's one problem. If we take these and substitute them back into Maxwell's curl equation, which is the curl of H has to equal to the partial of the electric field with respect to time, guess what? This does not equal. This does not satisfy Maxwell's equations. So therefore we have a problem. These equations are not valid, and so they will not accurately describe, in general, our electromagnetic field that is generated from this antenna. So what are we to do? Well, to remedy this, and again, you will see how this is done in a real antennas course or a graduate level antennas course. When we do, we come up with these equations. So they are our original equations, but we've added these additional equations to account for some different things that you'd get into in an antennas course. So you can see the original equation is still there, but we now have this R3 and R squared terms and this R term all in our equations. So these equations do describe our electromagnetic field, the electric field and magnetic field from the antenna, and they do satisfy Maxwell's equations, the curl of H equaling to the permittivity times the partial of E with respect to T. And feel free to test that out if you want, and but I have to just ask you to trust me on that again for sake of time at this point. So as I said, these are the general equations. They satisfy Maxwell's equations, and this is the general solution for a Hertzian dipole antenna. And that's the only antenna at this point. You have to rederive this for each different type of antennas. Luckily for us, for all the common antennas, these have already been derived, and you can look them up if you need them, if and when you need them. So I do want to look at a couple of special cases here, and this is true for all antennas and for electromagnetics in general, and that is we take note that when the radius, that is the distance away from our antenna, and we look at it in terms of, we say it's small. Well, what do we mean small? Well, we mean that if you take the phase constant times the radius, if that's much, much less than 1, then these equations can be reduced, and this is what they reduce to. And so these special cases for this near field, or excuse me, for when R is small, we refer to these as the near field equations. So if you are in a situation where you're working with electromagnetic fields and someone starts talking about the near field, this is what they're talking about, these approximations of the electric and magnetic field equations that are considered close to our whatever we're radiating, an antenna or transmission line or whatever. And so these are very useful in dealing with close radiation. What are some applications of that? Well, If you were dealing with different types of imaging, which that's a lot of what I've done. I've done some in my doctorate work with inverse imaging. We had to use the near field equations, and this could be for things such as a CAT scan or an MRI scan device in medical imaging. So it's a huge field right now, and there's a lot going on with that. So you'll see the application of these equations for those situations. Of course, the opposite of that is when R is large, and so again, when beta R, that product is much, much greater than 1, the equations reduce in a different way, and that is to these equations here. And so these are often referred to as the Farfield equations. And so these are the most common when dealing with long-range transmission, such as antennas. And so these are the equations that we'll probably look at the most for the remainder of the course when dealing with these antennas. So I did want to show you a couple of diagrams to kind of show you that fringe effect. So instead of the nice plane waves that we had before, when we have some type of generator that's sending a signal out to our antenna, you can see that these fields start to form in between. So you got these transmission lines, and so it's just a matter of really just splitting that transmission line apart until they get usually right angles when we're dealing with the Hertzian dipoles. And so you can see it creates this wave, and as it starts to radiate, it's not a perfect plane wave, and it does have fringe on there, but it is pretty close, especially as you get further and further out. We can approximate this as a plane wave for most applications. Here's another look at that phenomenon. As you see, if we had that perfect dipole and we have those charges going back and forth, you can see they start to create this. It's almost like blowing a bubble, and some people even use that analogy that this is an electromagnetic bubble now. If we had some source pushing it out, which would be our source, our generator source back over here, and so this just repeats over and over and over and creates those waves and radiates it, and we can transmit that and use it to transmit information, which is the big deal, right? Your cell phone, your Wi-Fi, all these things, they use these concepts, and this is how that does that. And you have the tools that you can make those calculations and design different things for that. So we'll continue our look with antennas moving forward, some different applications of that.